Welcome to this educational video where we'll explore the volume of a hemisphere. Today, we're going to master an important concept in three-dimensional geometry that has many practical applications in our world. A hemisphere is simply half of a sphere, like cutting a ball perfectly in half. Imagine taking a basketball and slicing it right through the middle. The result is a hemisphere, a three-dimensional shape with a flat circular base and a curved surface. This shape appears everywhere in our daily lives. Understanding how to calculate the volume of a hemisphere is useful in many real-world applications. Architects use it when designing domes, engineers need it for storage tanks, and manufacturers use it for bowls and containers. In this video series, we'll break down the concept step by step, providing clear explanations, visuals, and examples to help you master this geometric concept. We'll define what a hemisphere is, derive the volume formula, and work through practical examples together. By the end of this series, you'll have the confidence and skills to calculate hemisphere volumes in any situation. So grab your calculator and get ready to explore the fascinating world of three-dimensional geometry. Now that we understand what a hemisphere is, we need to learn the mathematical formula that allows us to calculate its volume. The volume formula is the key tool we'll use in all our calculations. The volume of a hemisphere is calculated using this specific formula. Let me show you the complete formula first, and then we'll break down each component. Let's break down each component of this formula. V represents the volume we're trying to find. This is what we're solving for, the amount of space inside the hemisphere. The R represents the radius of the hemisphere. This is the distance from the center of the flat circular base to any point on the curved edge. Notice that r appears with an exponent of 3. Pi, represented by the Greek letter pi, is a mathematical constant approximately equal to 3.14159. Pi appears in all formulas involving circles and spheres because of their curved nature. The fraction 2/3 tells us we're taking 2/3 of something. But 2/3 of what? This is where the connection to a full sphere becomes important. To understand where this formula comes from, we need to look at the volume formula for a complete sphere. A full sphere has the volume formula V equals 4/3 pi r³. Since a hemisphere is exactly half of a sphere, we might think we just divide the sphere formula by 2. Let's see what happens when we do that mathematically. When we multiply the fractions 1/2 times 4/3, we get 4/6. But 4/6 simplifies to 2/3. Which gives us our hemisphere formula. Therefore, the volume of a hemisphere equals 2/3 pi r³. This makes perfect mathematical sense. We're taking 2/3 of the sphere's volume, not just half. Remember these important points about the formula. First, the radius must be cubed, multiplied by itself 3 times. Second, the result will always be in cubic units, such as cubic centimeters or cubic meters. Now that we understand the formula and where it comes from, we're ready to use it to solve problems. In the next section, we'll work through our first example calculation step by step. Now we'll work through our first example. We need to find the volume of a hemisphere when we're given the radius of 5 centimeters. Step 1. We start with our hemisphere volume formula. V equals 2/3 times pi times r³. This is the formula we derived from the sphere volume by taking exactly half. Step 2. We substitute our given value. We know that r equals 5 centimeters, so we replace r in our formula with 5. This gives us V equals 2/3 pi times 5³. Step 3, we calculate 5³. 5³ means 5 times 5 times 5, which equals 125. So now our formula becomes V equals 2/3 pi times 125. Step 4, we multiply 2/3 times 125. When we multiply a fraction by a whole number, we multiply the numerator by that number. So 2 times 125 equals 250, giving us 250 over 3. Our formula is now V equals 250 over 3 times pi. Step 5, we calculate the final numerical value. 250 divided by 3 is approximately 83.33. When we multiply this by pi, which is approximately 3.4159, we get approximately 261.8. So our final answer is V equals approximately 261.8 cubic centimeters. Always remember to include the proper units in your final answer. Since we're calculating volume and our radius was in centimeters, our volume is measured in cubic centimeters. Now we'll work through our second example. We need to find the volume of a hemisphere when we're given the diameter instead of the radius. The key insight here is that our volume formula requires the radius, but we're given the diameter. We must first convert the diameter to radius before we can apply the formula. We substitute our diameter value of 10 units into this conversion formula. Dividing 10 by 2 gives us a radius of 5 units. Now that we have the radius, we can move to step 2 and apply our volume formula. We substitute our radius value of 5 units into the volume formula. First, we calculate 5 cubed. 5 to the third power equals 5 times 5 times 5, which equals 125. Next, we multiply 2 times 125, which equals 250. Now we divide 250 by 3 to get approximately 83.33, then multiply by pi. Finally, multiplying by pi, which is approximately 3.14159, gives us our final answer. Notice the critical step in this problem. We had to convert the diameter to radius first. This is a common requirement since the volume formula specifically uses the radius, not the diameter. The conversion step is essential because the volume formula is derived specifically for the radius. Missing this step is one of the most common mistakes students make when working with hemisphere problems. Now for our third example, we'll solve a real-world application problem. A hemispherical bowl has an inner radius of 4 inches, and we need to find how much water it can contain. Here we have a hemispherical bowl. The inner radius is 4 inches, which means the distance from the center of the circular base to the edge is 4 inches. First, let's identify our given information. We have a hemispherical bowl with an inner radius of 4 inches, and we need to find the volume of water it can contain. Step 1, we use the hemisphere volume formula. V equals 2/3 times pi times r cubed. Step 2. Now we substitute our radius value of 4 inches into the formula. V equals 2/3 times pi times 4 cubed. Step 3. We need to calculate 4 cubed. 4 cubed equals 4 times 4 times 4, which equals 64. So our formula becomes V equals 2/3 times pi times 64. Step 4. Now we complete the calculation. V equals 2/3 times pi times 64. This becomes 2 times 64 divided by 3 times pi. That's 128 divided by 3 times pi. Using pi approximately equals 3.14159, we get approximately 134.04 cubic inches. What does this result mean in practical terms? The hemispherical bowl can hold approximately 134.04 cubic inches of water. This information is valuable for cooking applications, determining serving sizes, or understanding storage capacity. In real-world scenarios, knowing the volume helps us understand exactly how much liquid the bowl can contain. This example demonstrates how hemisphere volume calculations apply to everyday objects. Whether you're designing containers, calculating liquid capacity, or solving engineering problems, the same mathematical principles apply. Now that we understand how to calculate hemisphere volume, where do we actually use these calculations in the real world? Hemisphere volume is crucial across many professional fields, from designing buildings to optimizing industrial systems. In architecture, hemisphere volume calculations are essential for designing domes and observatories. Architects need to know the internal volume to plan structural supports, estimate materials, and ensure proper acoustics. In engineering, hemisphere volume is critical for designing tanks and containers. Many storage tanks have hemispherical ends to distribute pressure evenly and maximize storage capacity while minimizing material usage. HVAC engineers use hemisphere volume calculations when designing heating and cooling systems for dome-shaped buildings. They need to know the exact air volume to properly size equipment and ensure efficient climate control. In physics, hemisphere volume calculations help determine the volume of fluids and gases in hemispherical containers. This is important for pressure calculations, fluid dynamics, and understanding how substances behave in curved containers. As we can see, hemisphere volume calculations are fundamental across many professional fields. Whether you're designing buildings, optimizing industrial systems, planning HVAC installations, or conducting physics experiments, understanding how to calculate hemisphere volume is an essential skill that connects mathematics to real-world problem solving. Before we wrap up, here are some essential tips and tricks to help you master hemisphere volume calculations and avoid common mistakes. Tip number 1. Always make sure you're using the radius in your formula, not the diameter. Remember, if you're given the diameter, divide by 2 to get the radius. Tip number 2. Always double-check your units. Make sure all measurements are in the same units before calculating, and remember that volume is always measured in cubic units. In today's world, modern CAD software and three-dimensional modeling tools are making it easier than ever to design and analyze complex hemispherical structures in architecture and engineering. By mastering hemisphere volume calculations, you're not just learning a formula, you're developing critical geometric understanding and problem-solving skills that apply to many real-world challenges. Remember, the key formula we've been working with is V equals 2/3 πr³. This simple yet powerful formula opens doors to understanding three-dimensional geometry. Thank you for joining me on this mathematical journey through hemisphere volumes. If this video helped you understand the concept better, please give it a thumbs up and subscribe for more educational content. Leave a comment if you have questions or suggestions for future topics. Keep practicing, and remember, mathematics is all around us, waiting to be discovered.